this is the final project, and the reason why I choose bloom filter is because it sounds like flowers, and then it turned out that it has nothing to do with that. So the outline is background, and then the pseudocode, and then I'll illustrate the idea of this algorithm with the illustration that I made, and then how to optimize this algorithm, and then demonstrate a little bit of the code snippets, and then analyze the time and space complexity. In the end, if time allows, there will be demo to show before and after the optimization, and I will talk about the application of how widely used this bloom filter is. So, where and how did this algorithm come from? This bloom filter was invented by Mr. Bloom, so it was called bloom filter. It has nothing to do with flowers. And why did he want to solve? Why did he need this algorithm, or why did he want to invent an algorithm? Because back at 1970 here, there is an issue that they need to efficiently check for the existence of elements in a large set with limited memory resources. When I read his paper, I couldn't help but wonder, well, isn't it the same problem that we're facing today? So it's quite interesting. And his paper is called Space-Time Trade-Offs in Hash Coding with Allowable Errors, with 5 pages, very concise. I highly recommend that. And so how did he actually implement that? He then invented this bloom filter, and it is a space-efficient probabilistic data structure. And later on, I will explain what probabilistic means, because this was also a new idea for me. All right. The pseudocode is that there are 3 main components, let's say, of this pseudocode for building up a bloom filter. First, we have initialize, and then we have this insertion of the elements into the array, and then we perform the checking thing, like we check if this element is contained in this array or not. And how does it go? For the initialize phase, we create a bit array of size m, and we initialize them first with all zeros, and then we choose k hash functions. Then for the insertion, it's an iteration loop. We compute for each hash function h, we compute hash values for the elements, and then we map hash value to an index in the bit array, and then we set the corresponding bit to 1. And for the containing part, so that means we're checking if this element is contained in this bit array or not. Same as before, we for each hash function h, we calculate again the hash value for the element, and then we map the hash value to an index in the bit array. So if this bit at index in the bit array is 0, we return false. That means this element definitely is not present in this bit array. But otherwise, we return true, which means this element may be present in this bit array, or may not be present. And this is actually where this probabilistic comes from, because we are not sure. And this is I think Achilles heel for the bloom filter. So in order to make everyone better understand what I just talked about for the pseudocode, I made some illustration, easy or metaphoric ones. Suppose that now we have a bit array of 21 elements from 0 to 20, and we choose 2 hash functions, 1 and 2. And then we have three objects that we actually want to store into the hash functions. So we throw this cat object into both 1 and 2 hash functions, and then we got number 2 and number 6. So what do we do with that? We go to the bit array and then found the index number 2 and turn the 0 into 1. Same for 6. So we go to the element 6 and turn the number 0 into 1, and so on and so on. And you might wonder, like, hey, dog and rat here are kind of hashing collision at 10 because they're both storing at 1. But this is nothing to do with, we don't have to concern about it right now because we're in the storing phase. The problem will only occur when we are retrieving informations. Okay. And now we are in the content or checking phase. We want to use the bit array that we just built up to check if dog, cow, and hen actually exist in the bit array or not. So we use the same hash functions 1 and 2, and we check, and when we throw this dog object into the hash functions again, we got 4 and 10. So we go to position 4, and it's 1. And we go to position 10, it's 1 as well. So the dog exists in this bit array. And for cow, let's see. For the position 9, it's 0. For position 20, it's 0. So no, cow does not exist. And for hen, we go to position 2 and 19 to see, okay, it's 1 and 19 is 1. So it exists. But wait a minute, we didn't put any hen inside, we didn't put any hen just yet. So this is called a false positive. It actually tells us that yes, this hen exists, but when we examine further, we realize that hen does not exist in this bit array. And this is the false positive and also the probabilistic nature of this algorithm. So how do we optimize that? In the paper of Mr. Bloom, there is this optimization function here, which is n over m raised to the power of log k to lower down the false positive possibilities. So m is the number of bits in the bit array, and n is the number of elements to be stored in the array. K is the number of hash functions. In order for these optimization functions to be as little as possible, we have to raise the K up and also M up. Why? Because N will always be larger than M, which means this one will always be larger than 1. If this number will always be larger than 1, then we had better lower down this log K to as small as possible. No, sorry, I think I made a mistake. Because the n is the number of elements to be stored in the array, and then m is the number of bit in the array. So m would always be larger than m. So this number would always be smaller than 1. And if we want this number to be close to 0, then log n has to be as big as possible. So we raise k and we raise m. That means we raise the number of hash functions, and also we raise the number of bits in the bit array. And for analyze, from that pseudocode, we can analyze already the time complexity and space complexity. So during the insertion phase, it's in the order of k because during insertion, the Bloom filter applies k hash functions to compute hash values for the elements. And each hash function operation contributes to the time complexity. So that is why during the insertion phase, it's the order of k. And for this containing part, which is checking whether this element exists in the bit array or not, it's in the order of k because in the checking part, the Bloom filter applies k hash functions to check if the element is present in the set, and each hash function operation also contributes to the time complexity. So overall, this time complexity is in the order of k, and space complexity is in proportion to the size of the bit array. So that means it is in the order of m. Right. And then comes the Bloom filter. Code snippets. We can do some fine tuning, just like the function that I just showed, to optimize this Bloom filter, and this is basically how it looks like: initialize, and then insertion, and then contents. Okay, and I want to show a little bit of how before and after the changing hash function numbers and bit array size can greatly reduce the probability false positive rates. So can you guys see the Jupyter notebook?
No, I cannot.
Okay. Then I stop sharing again and I share my entire screen. Oh, but Carl, I cannot. Oh, here. Sorry. Entire screen. Okay. So this is actually the whole function of Bloom filter, and I want to run it now. Each time I just choose random numbers of initialization. So every time it runs differently results. Before fine-tuning, the false positive rate is 1.8%. And after the false positive rate, it is 1.0%. So it has been reduced greatly, whereas the time taken is probably the same, like 0.004, 0.0047. And you can see that what did I do? I do the bit array size. It's 1283 bytes, and I double it to 2533 bytes. So I increase the memory. That is a trade-off that this Bloom filter has to bear, I guess, because when you lower down the false positive rate, you also are increasing the memory size, right? Stop here and go. So the common applications for the Bloom filters are three systems: the caching, and the spelling, and networking. Caching systems is just, well, people use or being used every day. We employ a Bloom filter to check, or the company use a Bloom filter to check whether a requested item is present in the cache before accessing slower storage. Or we use multiple hash functions to map cached items to positions in the Bloom filter's bit array, and that facilitates quick lookups. Another spell checking is more for dictionary thing, like use Bloom filter to efficiently determine if a word exists in a dictionary or a corpus. That's for NLP mainly. And you can also apply various hash functions to generate indices in the Bloom filter, allowing for rapid verification of word existence without exhaustive searches. And I guess network routing is most relevant for me, at least myself. Network routing in Bloom filter application is that we implement the Bloom filters to assist in routing decisions by quickly determining if a destination IP address is within a particular network range. And we apply multiple hash functions again to map IP addresses to positions in the Bloom filter, and that helps in efficient and scalable routing table lookups. So if you would like to read this paper, highly recommend it. Space-time trade-offs in hash coding with allowable errors. And this is the end of my presentation. Thank you very much.
Hey, great. Thank you very much, Stacy.